In mathematics, a vector is a geometric entity that has both magnitude and direction. It is represented as an arrow with a starting point, initial point, and an ending point, terminal point. The length of the arrow corresponds to the vector's magnitude, while the direction in which the arrow points represents the vector's direction. Vectors are fundamental in various fields, particularly in physics and engineering, where they are used to represent physical quantities that have both magnitude and direction, such as displacement, velocity, acceleration, and force. Here's a more detailed breakdown of a vector's properties. Magnitude: this is a measure of the vector's size or length. It is a scalar quantity, which means it has only magnitude and no direction. Direction: this indicates the path along which the vector acts. It is specified by the angle the vector makes with a reference axis or by its component along the coordinate axis. Initial point: the starting point of the vector, often denoted as the tail. Terminal point: the ending point of the vector, often referred to as the head. Vectors can be represented in various forms, such as bold lowercase letters, like a; arrow notation, like \vic a; component form, like \vic a equals a underscore I backslash hat I plus a underscore j backslash hat j plus a underscore k backslash hat k, where a underscore I, a underscore j, and a underscore k are the scalar components of the vector along the x, y, and z axes, respectively, and backslash hat I backslash hat j and backslash hat k are the unit vectors in the direction of the respective axes. Vectors can undergo various operations, such as addition, subtraction, and multiplication by a scalar, which follow specific rules that maintain the geometric nature of vectors. For example, when adding two vectors, you place the tail of the second vector at the head of the first and draw a new vector from the tail of the first to the head of the second. This is known as the triangle rule of vector addition. Vectors are different from scalars, which are quantities that have only magnitude and no direction, such as temperature or mass 12. For a practical example, consider a vector representing a force of 10 newtons acting northeast. The magnitude of this vector is 10 newtons, and its direction is northeast. If we were to represent this vector in a coordinate system, we might break it down into its eastward and northward components, each of which would be a scalar multiple of the unit vectors in the east and north directions too. Vectors are a powerful tool in mathematics and science because they concisely capture both the how much and which way aspects of physical quantities. Certainly, vectors are used in physics to represent any quantity that has both magnitude and direction. Here's an example involving velocity. Imagine you're driving a car on a straight road. Your velocity is a vector quantity because it describes not only how fast you're going, speed, but also the direction of your travel. If your speedometer reads 60 km per hour, km/h, that's the magnitude of your velocity vector. If you're driving north, then north is the direction of your velocity vector. Now, let's say you make a turn and start heading northeast while maintaining the same speed. Your velocity vector has changed because your direction has changed, even though the magnitude remains the same. If we were to draw this, we'd have an arrow pointing northeast with a length proportional to 60 km per hour. In physics problems, vectors are crucial for understanding motion. For instance, if you throw a ball, the ball's path can be analyzed using vectors for its velocity at different points, the gravitational force acting on it, and its displacement from the starting point. Each of these quantities can be represented by vectors, and by using vector addition and subtraction, we can predict the ball's trajectory and final position. Vectors also play a key role in fields like electromagnetism, where they are used to represent quantities like electric fields, magnetic fields, and forces between charged particles. For example, the electric field around a charged particle can be represented by vectors pointing away from or towards the particle, with their magnitude representing the strength of the field at different points in space. A vector space, also known as a linear space, is a fundamental concept in mathematics, particularly in linear algebra. It is a collection of objects called vectors, which can be added together and multiplied by scalars, where scalars are elements of a field, often real or complex numbers. The operations of vector addition and scalar multiplication must satisfy certain axioms that give the structure of a vector space. Here are the key properties and operations that define a vector space. Closure under addition: if \vic u and \vic v are vectors in the vector space V, then their sum \vic u plus \vic v is also in V. Closure under scalar multiplication: if C is a scalar and \vic v is a vector in V, then the product C \vic v is also in V. Commutativity of addition for any vectors \vic u and \vic v in v \vic u plus \vic v equals \vic v plus \vic u. Associativity of addition for any vectors \vic u \vic v and \vic w in v \vic u plus \vic v plus \vic w equals \vic u plus \vic v plus \vic w. Additive identity: there exists a vector \vic 0 in v called the zero vector, such that \vic v plus \vic 0 equals \vic v for all \vic v in v. Additive inverse: for every vector \vic v in v, there exists a vector \vic v in v such that \vic v plus \vic v equals \vic 0. Multiplicative identity: for every vector \vic v in v, 1 \vic v equals \vic v, where 1 is the multiplicative identity in the field of scalars. Distributivity of scalars over vector addition: for any scalar c and vectors \vic u and \vic v in v, c \vic u plus \vic v equals c \vic u plus c \vic v. Distributivity of vector addition over scalar addition: for any scalars a and b and vector \vic v in v, a plus b \vic v equals a \vic v plus b \vic v. Associativity of scalar multiplication: for any scalars a and b and vector \vic v in v, a b \vic v equals a b \vic v. The simplest example of a vector space is the n-dimensional Euclidean space, denoted as \math r(n), where each vector is represented by a list of n real numbers, and the scalars are real numbers. The operations of addition and scalar multiplication are performed component-wise. Vector spaces can be more abstract, however, and do not necessarily have to be associated with geometric concepts like points in space. They can include function spaces, spaces of sequences, spaces of matrices, and many more, as long as the set of vectors and the operations defined on them satisfy the vector space axioms 1, 2, 3. In essence, vector spaces allow us to generalize the concept of vectors beyond simple arrows in space to include any set of objects that behave according to the rules of vector addition and scalar multiplication. This generalization is powerful and forms the basis for much of modern mathematics and physics. To determine if a set, along with its associated operations, satisfies the axioms of a vector space, you need to verify that all the axioms hold true for the elements within that set. Here's a step-by-step approach to checking the axioms. Closure under addition: verify that adding any two vectors from the set results in another vector that is also within the set. Closure under scalar multiplication: check that multiplying any vector by a scalar from the field associated with the vector space results in a vector that remains within the set. Commutativity of addition: ensure that the order of addition does not affect the result. \vic u plus \vic v equals \vic v plus \vic u for any vectors \vic u and \vic v in the set. Associativity of addition: confirm that the grouping of vectors during addition does not affect the sum \vic u plus \vic v plus \vic w equals \vic u plus \vic v plus \vic w. Existence of additive identity: identify the zero vector in the set such that adding it to any vector in the set does not change the vector \vic v plus \vic 0 equals \vic v. Existence of additive inverses: for every vector in the set, there should be another vector that, when added to it, results in the zero vector \vic v plus \vic v equals \vic 0. Distributivity of scalar multiplication over vector addition: check that a scalar distributed over a vector sum equals the sum of the scalar multiples. C \vic u plus \vic v equals c \vic u plus c \vic v. Distributivity of vector addition over scalar addition: ensure that the sum of scalars multiplied by a vector equals the sum of each scalar multiplied by the vector. A plus b \vic v equals a \vic v plus b \vic v. Associativity of scalar multiplication: confirm that the product of a scalar with a scalar multiple of a vector is the same as the scalar multiple of the scalar product. A b \vic v equals a b \vic v. Existence of multiplicative identity: verify that multiplying any vector by the scalar 1 does not change the vector 1 \vic v equals \vic v. You must test each axiom systematically for the set and operations in question. If even one axiom does not hold, the set is not a vector space. It's important to note that these checks must be made generally and not just for specific examples within the set 1, 2, 3, 4, 5. For example, consider the set of all 2x2 matrices with real entries under standard matrix addition and scalar multiplication. You would need to verify that all 10 axioms are satisfied for this set to be a vector space. This involves checking that the sum of any two matrices is another 2x2 matrix, that any matrix multiplied by a real number is still a 2x2 matrix, and so on for the other axioms. If all axioms are satisfied, then the set of 2x2 matrices with real entries is indeed a vector space. Certainly, an example of a set that isn't a vector space is the set of all 2x2 matrices with integer entries, denoted by m2\math_z. This set is not a vector space because it fails to satisfy the axiom of existence of additive inverses. In a vector space, every element must have an inverse such that their sum equals the zero vector. However, in the set m2\math_z, not every matrix has an inverse within the set of matrices with integer entries. For instance, the matrix \begin matrix 1 and 0\0 and 1\end matrix has an inverse in the set of all 2x2 matrices with real entries, but not in the set of matrices with only integer entries, because the inverse would require entries that are not integers 1. Another example is the set of all ordered pairs of positive real numbers. This set does not satisfy the vector space axioms because it does not include the zero vector, which would have both entries as 0, and it is not closed under scalar multiplication by negative numbers, which would result in non-positive entries too. These examples illustrate sets that, while they may satisfy some of the vector space axioms, do not fulfill all of them and therefore are not considered vector spaces. The concept of vectors, as we understand them today, has a rich history that dates back to the 19th century. The geometric representations of complex numbers in the early 19th century by mathematicians like Caspar Wessel, Jean-Robert Argand, and Carl Friedrich Gauss laid the groundwork for vectors, treating complex numbers as points in a two-dimensional plane, essentially as two-dimensional vectors 1. The term vector and the formal development of vector analysis, however, came later in the 19th century. This development is attributed to Josiah Willard Gibbs and Oliver Heaviside, who independently created vector analysis to articulate the new laws of electromagnetism discovered by James Clerk Maxwell II. Their work in the late 19th century formalized vectors as entities with both magnitude and direction, which could be used in mathematical and physical applications. Before this formalization, the concept of directed quantities was intuitively used in various forms. For example, the parallelogram law for vector addition was known but not formally defined as a vector operation. Isaac Newton, in his Principia Mathematica, dealt with quantities like velocity and force, which are now considered vectors, but he did not use the concept of a vector as it is defined today. The formalization of vectors and vector spaces provided a powerful language for expressing ideas in physics, engineering, and mathematics, and has become an indispensable tool in these fields. The work of Gibbs and Heaviside allowed for a more concise and powerful representation of physical laws, particularly those in electromagnetism, which heavily rely on vector quantities. The concept of vector spaces as abstract algebraic entities was first defined by the Italian mathematician Giuseppe Peano in 1881. Peano introduced the modern form of the axioms of a vector space, which are essential for the structure and operations within a vector space. However, the groundwork for the idea of vector spaces can be traced back to earlier mathematicians. The notion of vectors in 2- and 3-dimensional spaces, associated with a field of real numbers, was discussed by René Descartes and Pierre de Fermat in the context of coordinate geometry. They focused on points and graphing rather than on the abstract concept of vectors as we understand them today too. The realization that abstract vector spaces are abundant in mathematics and the focus on function spaces as vector spaces emerged in the late 19th century. The modern definition of vector spaces owes much to Peano's work, and the importance of function spaces as vector spaces was highlighted in the work of Henry Lebesgue. This was further formalized by David Hilbert and Stefan Banach in the 20th century, leading to the development of Hilbert and Banach spaces, which are now fundamental parts of graduate study in mathematics too. The development of vector spaces was motivated by various needs in mathematics and physics, including the representation of physical quantities and the manipulation and study of systems of linear equations. The concept of vector spaces is fundamental for linear algebra, which, together with the concept of matrices, provides a concise and synthetic way for these applications. 3. In summary, while Peano is credited with the formal definition of vector spaces in 1888, the evolution of the concept began much earlier and was influenced by the work of several mathematicians and the needs of different scientific fields. That was all. Goodbye.